All right, so we need to do the calculations from the specific heat of a metal lab. We got these calculations on Tuesday, the 4th. And so if you would please go ahead and go through, and you need to number or put a letter next to that line, and you're going to put a letter. We'll just go ahead and number all the way down with letters. This will help us to do some of the calculating. So the first thing we need to remember is what we were doing is heat was transferring. We use Q to represent heat. So we had heat that the water gained was equal to the heat that the metal lost. All right, so that's a positive Q is equal to Q, but it would have been a negative because it lost energy. So the first thing we need to do is calculate the energy that the water gained. Q of the water is equal to M times specific heat, mass times specific heat times the temperature change. So your mass is A, line A. Your temperature or your specific heat, we look up in a data table, and we have that data table right here. And it's the specific heat of water is 4.18 joules over grams degrees Celsius. That's in line A. And then our temperature change is line D. And it's going to be positive because the temperature increased, or we added energy in. So if we multiply that out, and I will use some data. So if we have the mass of the water is 195.23 grams times 4.18 joules over grams degrees Celsius. That's joules per grams degrees times degrees Celsius, because it's the energy it takes to change 1 gram 1 degree Celsius. And then our temperature change we're going to use is 2.4. Now those aren't going to match your numbers. You're going to have to look at your data table to get that information. And if we do the math for that, we come up with 1958.5 joules. That is equal to the energy that the metal lost. So we're going to take that number and we're going to write that down here. Q of metal is equal to mass times specific heat times temperature change. So we're going to write negative 1958.5 joules is equal to the mass of the water, and the mass of the metal, and the mass of the metal is 276.4 grams for the lab I'm using. Specific heat is what we're solving for, and temperature change went, in this case, from 101 to 25.5, so it was a change of 75.5 degrees Celsius. So we want to solve for the specific heat. Now, the first thing we should do, though, is go ahead and multiply 276.4 times 75.5. And when we do that, we get negative 2868.2 times the variable C. So now we're just in a math problem. Now we're just in a basic algebra problem So how do you solve for C by itself? Well, we divide both sides by 2868.2, and that would be that comes out to be 0.094 joules over grams degrees Celsius. Okay? Kind of an interesting number. Okay? Notice that they're both negative, so it comes out to be positive. So, the first question says, it asks what metal did we identify? And that was our beginning question. So we're going to make a claim. The metal that we tested had a specific heat of, and you're going to put your answer in, whatever you got. And you're going to go back to page 4. And you're going to look and see what is that closest to. And the one I just calculated was 0.098, 09 something. So if we round that up to 0.1, we come close to mercury. So the group I just used, their data that I used, they're going to say their specific heat matched mercury. You're going to look and see what is your specific heat match, and you're going to write down the one that it's closest, and then you're going to write its actual specific heat. Okay? The second piece, the question asks for possible sources of error. All right? Group 5 had, actually this is Group 5's data that I used, that they got very strange issues. One suggestion, though, would be timing. If you didn't time the, with the temperature, if you didn't let it time long enough till it topped off. That was one of the suggestions, which actually it's going to solve itself, because if you stop timing it, it may have continued to transfer heat, but it would have been fine. But that's a possible error, is when you took your temperatures. If you lost mass or gained mass of water specifically, that would be another possible source of error. The third question asks, if our body temperature is 98.6 and the room temperature is about 73 degrees Fahrenheit, why don't we equalize? We took that warm block and put it in the cool water, and the cool water warmed up a little bit and the block cooled down a bunch. Well, we're sitting in here kind of we're in a ocean of air. Why does the air not rise because of our temperature and we go down? Why does our temperature not go down? Well, the main reason is because we are warm-blooded mammals. We make our own heat. If you have ever watched any of the crime shows, one of the first things they do with the body is they take the internal temperature of it to figure out how long somebody's been dead. Okay? We're constantly making energy, so our energy is not going to our temperature is not going to drop to the temperature of the room. Now, you can get a room full of people and they can put off enough energy that they can bring the temperature of the room up. But we would have to put off so much energy if it's just one person in a room to bring the temperature up that's going to be highly unlikely. All right. Question 4 asked, how much energy is needed to raise the temperature of a 35-gram piece of brass from 23 Celsius to 70? So we're just going to use Q equals MCAT. This is the M. This is the delta T. And there's C. And you solve for Q. And that will be, you'll answer that in your lab notebook. And then for step 5, question 5, imagine you place a copper pot filled with water on the stove. After several minutes, the metal is too hot to touch, but the water is barely warm. Use the term specific heat in your answer. And that goes in your lab notebook as well. All right, once you've finished that, you'll turn that in. And we're going to go and look at notes about enthalpy. Okay. This is page 5 in your note set. Enthalpy is the energy content of a chemical change or of a chemical reaction. We use the term enthalpy because we're talking about energy that's coming from breaking and forming bonds rather than energy that's transferring. Although we use the term enthalpy when we talk about phase changes too. So you could use the term enthalpy instead of Q if you really wanted to. Or we could have never said heat, we could have said enthalpy for the whole chapter. All right. So when we talk about reactions that have a negative enthalpy, we're talking about exothermic reactions. Those are reactions where we are releasing energy into the environment. Energies that have reactions with a positive enthalpy are endothermic. They are absorbing energy from the environment or removing energy from the environment. So it's going from the environment into the system. This picture here we have energy graph drawn, and this is time, basically. If we start with water, in order to break the bonds between hydrogen and oxygen in the water molecules, we have to add that much energy, that total amount of energy. All right, once we get them all broken, they will reform, and they will reform as hydrogen and oxygen. But they don't give off very much energy as they reform. The bonds take in a lot of energy, but they don't give off as much energy reforming. So we end up having an overall amount of energy that we added, or enthalpy that we added, and it's a positive enthalpy. An exothermic, we release energy, and it involves a negative change. So if we take the same reaction, only reverse it, we can easily break the hydrogen and oxygen bonds, and then once they reform into water, that gives off a tremendous amount of energy. It's a much more stable product, and so we end up releasing energy. This energy gets made up, and we have all this extra energy left over that gets put off into the environment. Whereas back here, we had this amount of energy that we had to add in to get it to go. Thermochemistry is the science of measuring the heat of a chemical reaction or physical change. A calorimeter is a device used to measure the heat absorbed or released. And when we did the lab with the styrofoam cups were our calorimeter. All right.